Okay, everyone. Uh, let's start the active listening section. We try to solve some problem, and this problem would be some hint to the final exam in this subject. Okay, let's share the screen. Hmm? Video is paused. Oh, okay, just normal. And then here the gaps. Uh, I will answer just only for uh, the the problems that I aim to apply to the final exam. The rest is for you guys to do, and there is some answers in the WE learning. So if you would like to understand more in some challenge problems, you can do it by yourself, and then you can verify your answer with uh, the answer that I already attached on e-learning. Okay. Okay. For this one, the first one is very easy. That is why um I would like to do this, and you guys would be happy. Okay, for this one, balloon, right, has a constant pressure and temperature. So constant P, just fix P and fix T. How many molecules? How many molecules? If I ask for the total number, be inserted to the balloon that does 1 kilojoules of work on the balloon. Okay, as you can see that I have been explained about the work on the balloon, right? The work on the balloon, when you interpret this term, it means volume increase. Volume increase. Okay. It for this one, if you would like to find the work that represent the balloon that increase volume, by the definition of work is P multiply delta V, right? Ah, and we all know that it is P. Okay. The P delta V must be equal to delta PV. For this case, that we fix pressure, okay? And it equal to delta N T from the relation of ideal gas. And because in this case, T is fixed, then for this case, R and T would be out of the delta. There must be only delta N. Okay. And R is the constant. You don't have to concern about remembering these values, because in the exam, I will always put the number of every variables and formulas into your problems. Okay. For this case, R 8.314 joules per mole Kelvin. Okay. And T is 20 degrees Celsius. You have to convert it into Kelvin. You have to add 273 220 into the Kelvin. And you would like to find delta N, which is the number of the molecule of air that you have to insert into the ball. To that, to do what? To do 1 kilojoule. So this would be 1 kilojoules by 8.314 joules per mole Kelvin and 793. So the rest is for your calculator, and you will get around 0.410 moles. That is the final answer for this question. So for this one, you have to understand what they want to know, which is the number of the molecule of the air that would like to be inserted into the balloon to do the 1 kilojoules of work. Okay, under the pressure and temperature fixed. Okay, and for this one, for the second one, if you have the ideal gas, which is kept in some container, 5 liter. Here got the volume. Okay, 5 liter. And oh, the temperature around 50 degrees Celsius. Oh, and pressure as well, right here. They would like to know the molecules inside the container. This is straightforward problem because if you know about the relation of the ideal gas, you put it out. You know pressure, which is right here. Which is right here. 796 tall. And you can convert it into the SI unit later. Okay. You have the volume right here. You don't know the number of the molecules. You know the R. You know temperature because they already have. But you have to know how to convert, okay? How to convert the unit into the unit that you can comprehend. In this case, N equal to PV by RT. Okay, the pressure is 796 torr, which is totally not the unit in SI unit. So we would like to get rid of torr, right? Then torr at the hour and Newton per meter square. On top, right here, we have this number and around this number. So this is for pressure only. And the volume, luckily, that they already give us in the unit of the SI unit. And the RT is the same, is 8.314 joules per Kelvin mole here. And the temperature, you have to add 273 to convert it into Kelvin. Just it. Okay? Just it. So the rest is about the calculator, okay? You have to add this and get it into 323 Kelvin. And the final answer for this, okay, before, just for you guys to check, the pressure would be around here. The volume might be converted into scientific way. And here, when the unit is in mole. So the final answer for this case is 0.1976 mole. It's less than 0.2 a little bit. Okay. And next, uh, this one I skipped, but you can see the answer on the e-learning. And this one is also challenging. You should try in your free time. Uh, this one is about the calculation of the pressure that press on you when you dive below the surface of the water. And there is two ways to calculate this. I would like to go from the direct way. Okay, from the direct way. Okay. Uh, a scuba diver breathes air from a tank that has pressure regulator to feed the ambient pressure. The diver is at 30 meters below the surface. Here is the surface of water. And here is a diver with the air tank. Okay. So at 30 meters, uh, at that time, the volume of his lung is around 6 liters at maximum. Okay. If he decide to rise up, mean go up immediately. This is a keyword. Go up immediately. What volume of his lung will be? Okay. Uh, what do we have here? We have volume, right? We have you can you can find the pressure here. I would call V1. Okay. And V lung is called V1. Okay. When they go upward immediately at the surface, it would be P2 and V2. We would like to know P2. Okay, let's see what's the pressure at the surface of the water. Uh, P2 is 1 atm. Hmm? It's 1 atm. While P1 could be P of the air, right? Plus P of the gauge. So P of the air on top of the surface is P2 or P atm, which is 1 atm, right? And P gauge is around you can find rho g h. In this case, 1 atm I approximated into 10 to 5 Newton per meter square. So I will give you exactly value of 1 atm when you have to deal with this in the exam, okay? And the rho gs is here. Should 10. and H is 30 meters. So the final pressure for this one is 4 10 to 5 Newton per meter square. Because we assume that the temperature doesn't change a lot, so we can use the reduced law, not just the full form of uh, not just the full form of the ideal gas. You can neglect temperature right here, because we as oh sorry. Okay. Hmm? Okay, right now, it come back to normal. P1 is equal to 4 times 10 to 5 Newton per meter square. And V1 is about 6 liter. And P2 is 10 to 5 Newton per meter square. We would like to find the volume of V2. And here we got V2 around 24 lit. You can answer in this unit, or maybe you just change from this to this later. So I will give you the conversion. Okay. You might ask that is it necessary to change the unit of into SI unit? For this case, uh, the relation right here is P and V. That is the multiply. So you don't have to change the unit to SI unit. No need. No need. No need. Because there is the multiplication. So the unit always cancel out each other. Mhm. Except you use the full form of ideal gas. For example, this one. You use the full form and you need the exact one because the tau right here could not be get rid of if you don't use this identity. And the temperature as well, if you have the 50 degrees Celsius, it cannot convert into Kelvin if you don't add 273 to this equation. And this is the first way to do. And another way is very easy because you can approximation the pressure one. As you can see that I always tell you that every 10 meters, the gauge pressure increase 1 atm, right? So P2 equal to 1 atm. Then P1 must be PATM plus what? 30 meters. 30 meters mean 3 times of PATM, right? It would be 4 of the PATM. And when you apply to P1 V1 equal to P2 V2, P1 is 4 of PATM, right? And V1 is around 6 liter. And P2 is 1. Right now, I can write ATM. ATM. So V2 is around 24 liter because the unit of ATM cancel each other, leaving just only liter and the number 4 times 6, 24 liters. And you can see that if you use this phrase, if you use this phrase, you can calculate immediately. That's it. No need to convert something blah, 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 blah. Okay, that is a technique. And the last one, I would like to give you to think about this, to practice, is this one. Just imagine that a consumption of 14.5 liters of oxygen per hour is equivalent to how many molecules per second? Can you guys do it? Okay. If there is a machine or body or something that can consume 14.5 liters of oxygen per hour, so can you imagine how much molecules that can be fed into that machine per second? Okay, this is totally the unit change, but you have to add physics into this. Okay, for example, the concentrate right here is 14.5 liters per hour, right? You might would like to change into the unit that uh, we we get used to. For example, we don't use liters in SI unit, right? We just change from liter into cubic meters. 1 liters is 2 that's 3. An hour should be converted into a second with 1 hour, 3,600 seconds right here. Okay, just leave it to be right here. It is earlier, but there is no way that you can convert this unit into molecule if you don't know physics, right? Because it is a volume. Right here, no matter what number is, this is the unit of volume per second. The way to convert from the volume into the molecules, you need the relation of gas. And yes, in this case, you need full form of ideal gas. PV equal nRT. Okay? You need to convert from V into N. Then you write N in this part, PV by RT. And because this doesn't tell you anything about the pressure, I assume that it is on the atmosphere pressure. Oh, here 760 toll, which can be converted into here Newton per meter square. Okay, and the volume right here is 14.5 times 10 to minus 3 cubic meters by 8.314 joules per Kelvin mole. And the temperature right here at 0 degrees Celsius is 273 Kelvin. It's very important because you use the Kelvin unit. Okay. And due to the rate, they want you to calculate the number of molecules per second. So you have to find the ratio of n per time duration, right? Which is all this number. Which is all this number. And divided by 1 hour. And right now you can convert 1 hour into second, which is 3,600 seconds. And the rest is about the calculator, which is 1.08 times 10 to 20 numbers per second. So they asked about the number of the molecules, not the moles. And here is the answer. The way to convert this. Oh, I made a conclusion. Sorry. Actually, if you calculate here, you will get 1.79 times 10 to minus mole per second. Because the unit of Newton per square meter and cubic meter combined to each other would cancel out this one, right? Kelvin, cancel Kelvin. Leave just only 1 by 1 mole, and 1 by 1 by second, right here. You can convert it into mole per second, right here. However, in this problem, they want to know about the molecules, not mole. You have to put from this number into real number. 1 mole equal to 6.02 10 to 23. And your final answer is 1.08 10 to 20 number per second. And that's it. This is how to convert from the rate that in the unit of volume per second into molecules per second. And the way to convert it, you have to use the ideal gas. Okay? You change from V into N. That's it. And here, that is the end of the today class. And I would like to thank you all to listen to me here. I hope you guys are safe from the flooding, from anything that come to challenge us. And if you would like to ask me anything, you can ask me via the Facebook, and I will answer as fast as I can. Thank you, you guys.